Good morning, everyone. I'm Margi Leach. I have a primary background in teaching, but I've also taught up to Year 10. I'm going to share with you today a part of my learning journey of supporting students who struggle with maths. I hope you enjoy the session. It might go a little bit faster. Let's see. Hold on to your hats. You'll enjoy it. So what makes maths such a challenge? Well, symbols represent language and number ideas, and a lot of children don't understand the representational nature of symbols. There's lots of things to remember while you're working with maths. There are a lot of rules and strategies to take on board and understand. Sometimes you haven't reached the point where concepts have been taught to you, or they have been and you haven't understood them. And there's a lot of memory demand that happens in mathematics. You may also have dyscalculia, and it can be either some of these or all of these. Now, for more information, go to the Scottish Dyscalculia organisation, and that they will unpack this a lot more for you. But basically, it impacts on memory, understanding what subitizing is, estimating skill, and then ordering sequences, recognizing and understanding number symbols, how numbers relate to each other, especially the numerals and the words. And then just figuring out basic facts and relationships of numbers, applying the number skills and everyday tasks. And there's one more aspect that is not listed here, and that for some people, some numbers may not exist. So we know this is particularly true for people who have Down syndrome, that number 4 and often number 7 and number 11 can be a problem. But it can also be normal developing people can have this difficulty. I've met several secondary teachers who have admitted to me that 23 was missing for them. So it's not an unusual thing. We recognize that it's approximately the same occurrence in the community as dyslexia. And some people can be gifted with dyslexia as well as dyscalculia. So solutions. We need to support the learners to connect with the abstractness of maths, using manipulatives or visuals, and teach the language of maths. And so often we skip both of those ideas and children are truly mystified by the whole thing. And of course, maths is really obvious. Now, I want to unpack these 3 points this morning. Let's start with numbers itself. Many students actually have no idea that numbers represent a group, the quantity or the amount. Secondly, they don't understand the language in maths of an adjective describing the group, as well as the verb of what you do with these things. So that's a total mystery for them. And we've got all sorts of numbers that increase in challenges. So if you really haven't understood the natural and whole numbers, these are going to be total mysteries and children just learn them by rote. So for some students, it's been a long struggle, and surprisingly, if you've got students who are struggling, it will all go back to the first 6 months when they were 5 years old at school. So here's an example that I came up today. And if we want mixed ability classrooms, we're going to have to think a little bit more outside the box. So this question came up on the NZ Maths Facebook group this week, and it was a perfect example of how to make learning accessible. So a teacher was asking, what method should I use to solve this problem? So here are some of the responses. So if you've got a student who's struggling with maths, would they have any idea what factorize is? Would they have any idea how you could square an n? How do you square an n? You could make a table and square it and difference. So you see, children really struggle with the language of maths. So here's what another teacher suggested. I would get them to look at pictures every time, and there's an example. So as soon as you look at the picture, you know, now I know what they're asking for. So now I can make sense of the symbols. So visuals are very powerful for everybody, not just children, but for adults as well. Maths is more than numbers and more than procedure. It's all about structure, logic, reason. So I want to start from the learner's beginning to unpack some of this to give you an idea maybe why your students are struggling. Think of 5 in your head. What does it look like? And you can put your responses in the chat box if you want to. Some people may think of 5 fingers. Some people may think of the numeral 5. Others may think of the word 5. Now we've got all different perceptions of what we think 5 is. Then trying to communicate just with words to children, they'll have no idea what you're talking about. We don't all see 5 the same way. And you can't actually show anyone what 5 is. So children at primary school have to put all of these concepts together to know that actually what 5 is, it's represented by these, by this shape, by that Cuisenaire rod, by tally marks, dice, fingers, and then actual things that they pick up and play with. That's the concept of 5. But you can't actually show it. You have to get something out to do it for you. So it's not surprising that there are confusions. For example, what is half of 8? Well, you could cut it across the top. You could cut it down the middle. How would I find half of 4? Well, that's a bit tricky. I could go diagonally, or I could cut the 3 in half. So you see, our language doesn't help us either, does it? Similarly, which number is the biggest? Well, font size, 5 is the biggest, but concept-wise, 10 is. So now let's think about subitizing and conservation of number, early skills. And we know from research that even animals and birds can subitize 3. We as human beings can subitize to 3. But there are some people who have difficulties subitizing more than that, and also different presentations of it. So if I present 3 vertically, what if I put it around horizontally? Is it still 3? What if I spread them out? Is it still 3? And children who are less than 5.5 or maybe less than 6 will typically say there are more there than here because they're spaced out more, take up more space. Similarly, if I put out counters of different colors, children may not see the connectedness to know that those are 3. So now let's think of a bigger group of 5, and it's clustered just randomly. If I put it into a circle, are they still the same value? Now, you may think this is, oh my gosh, everybody should get this, but go try it out on your 5-year-olds, even 4-year-olds, and see what you discover by observing them. So another challenge that we find is that children are asked to memorize 5 dots in a line, especially if they use the tens frames. But this often to confirm requires a bit of maths, either the 3 + 2 or the 4 + 1. And again, if I put it into different rotations, do I still recognize it? So it's interesting that as humans, we are made in a pattern. We love patterns, and patterns are easier to remember. Now, there's one pattern I haven't put up here, and that's the dice 5, because we all remember it. So a line is not so easy to remember as a clustered pattern. Let's think what else we do with numbers. We double them. So what does double mean? Unpacking that word, it means 2 of. Another challenge is counting on. We've got to remember one number and then add on to it step by step. That's a huge challenge. Whereas if children could just see that was a group of 3 and that was a group of 3, it requires much less memory to know that the total is 6. And again, if we've got different sizes, can they also be grouped? Yes, they can, because they all belong to the blue group. Now, there was a group of scientists looking at how we perceive things and came up with a theory called the Gestalt theory from Germany and Austria. And one of their research questions was to flash a light at people and then ask them how many lights. And everyone responded by saying there was only one. So again, when they showed them this flowers, they said, how many flowers? And they said, well, one bunch. So when we look at things, we don't look at all the parts. We look at the whole thing first. Similarly, when we listen to music, we don't isolate all the notes. We hear the melody. So then when we see those, we just say, oh, that's a group of 6. We don't see them individually, one by one. There's the link for you to look at later. So how do we learn? Well, memory is created through brain connections, and the stimulus, the senses, provide this information to us. While we're working, it goes into a working memory nature, which enables you to stay on task right now. Then when we go to sleep, it goes into our long-term memory. Then it comes back during the encoding, and we can retrieve it. Now, if you've got students who struggle with working memory, you'll need to find a sensory stimulus that is going to help them stay on task. So if they have auditory processing as an issue, you'll have to provide something tangible and visual. If they have difficulty with sleep, they may have sleep apnea, then that's going to impact on their long-term memory. So the idea then is that you're going to have to repeat and link what you taught yesterday to today. And it's very common that you're working with students and they can't remember things. So that's why Brunner discovered teaching in a spiral approach rather than blocks, just like Tabitha was talking about. When you get to the next block several months later, they can't remember it. So you need to keep it alive every week. Explicit teaching. Model with concrete resources, get them to copy with it, help them guide it into it, then give them independent practice, link with visual and abstract components, and provide all of the language. So all of these ideas, that's what explicit teaching and supported teaching looks like. So let's now look at the maths side of things. Well, what's that symbol? Because maths is full of symbols, isn't it? You've got no idea? Well, that's the same experience the child would have seeing that. So what do you think of that? That still gives you no idea what this is. That could be more helpful, couldn't it? So that's why visual and hands-on activities are so powerful for all learners. Now, in this wonderful report from Natalie Dent at the ministry, this lists all the things that you need to do, and I want to make a case for teaching the language in maths so that they can participate, and using multiple representations. There's the link that you can follow later. So why use structured manipulatives and structured teaching approach? To enable learning. And this is based on wide research from people over nearly 80 years, actually. So let's think about maths. It's abstract. What do you mean? Well, show me what 5 is. There you go. You have to use something. So numbers are concepts. Even the word concept sometimes is not understood by people. You've got to illustrate it. So let's think about the beginning. Children typically learn by chanting. They learn recognizing numerals. And then they look at and describe this group of stars, and they would call them 6 stars. Now we're beginning to understand from practice that this is now the challenge at the next step. We've got a group of 5 and a group of 1. Now we're going to combine the groups and have a greater group, and it's going to have a new name called 6. And this is often where children miss out on making that connection. So they have to practice, verbalize their names as nouns rather than describing adjectives. But notice what's happening with the groups. So adults need to set up purposeful play so that they can make those connections. And it's the beginning of algebra, isn't it? So linking symbols with naming groups. Now, counting is a process. And typically children count 1, 2, 3, 4, 5. And in doing so, they name this one as being 1, this one as being 2, this one as being 3, this one as being 4, and they're all isolated. What they're actually missing is that it's groups, that this itself is a group of 1, but this is actually the group of 2. It's that one that makes the group 2. It's this one that makes the group 3. It's this one that makes the group 4, etc. So when you're working with children with counting, put them into a box or a container or a circle ring so that idea of total and group or set is firm in their minds. Our New Zealand curriculum talks about exploring and using. So you can only explore with stuff. And we're going to look at patterns and relationships. So how do we explore abstract concepts? Give them pictures. Give them algebra tiles or counters or things to work with. Make it really obvious because we're wanting understanding. So here we have a group of 6 eggs. That's also a representation of 6. We've got 6 counters as it would fit on the tens frame, 6 on the dice or numicon patterns, 6 as a Cuisenaire rod, 6 as a word, and 6 as a numeral. We've also got 6 squares of something. And we can use place value equipment using these little cubes. So we want children now to combine all of that thinking to generalize that 6 can be made. And that's where some connections can be lost. Now, Jerome Bruner, in his studies and looking at how children learn English, is also the same in learning maths, that they start off with something concrete to hold on to, and then make the connections to pictures, and then the connections to the abstract. Now, in recent research, we've found that children with Down syndrome and maybe some children with autism skip this bit here and go straight from the concrete to the abstract. They can't relate so much to pictures, so be aware of that. Now, the foundations. Haylock and Coburn had another study and discovered that if we don't link up the language with the concrete experiences and provide pictures and for children to create pictures, then symbols don't make any sense. So here are some examples. We need to illustrate these for students. Now, in our younger years, we can use lots of concrete activities. That's why little children have so many toys. And then as we get older, we work more in the abstract, but use manipulatives every time you introduce or reconnect with previous learning or clarify a concept. So I'm now going to stop sharing and show you how you use this equipment to cover all of those points. So down on my table here, I have some structured apparatus already set out for you. And what this does is that it actually illustrates numbers from 1 through 10, and the children can get a concept of what a number line is. So they can see that as we move this direction of a number line, the groups are increasing, and this way they're decreasing. But we can also get an idea of consecutive numbers and the reason why, because there is a difference of 1 each time. So the logic of putting numbers together is easily seen. 4 obviously doesn't belong there because it's greater than this one. So that also helps children understand what greater than and what less than is. Now, when we think about these as being groups, children can get a great understanding, and I'm going to pick out the 6th one and illustrate this with 6 counters. Now, how many of these bottom shapes do I have here? I have 1. This is one group. So this is 1 of the 6, 2 of the 6, 3 of the 6, 4 of the 6, 5 of the 6, 6 of the 6. The whole group is covered. Now, just to make it easier, I'm going to switch this 1 counter with a 1 shape. When I hold it up, you can now see 1 over the top of the other. That's what 1/6 looks like. So 1/6 plus another 6 is going to make 2/6. So if I replace those 2 with this one, and then add another one, I can see that 2/6 plus 1/6 makes 3/6. If I replace that with that, I can see that 3/6 can fit on 2 times. So it has 2 names. It's called 3/6, but 1/2 because it's 1 of the 2. So you see, fractions is so easy to understand when you're using this equipment. Let's think about tenths. So if I have 2/10 plus 5/10, I'm creating 7/10. 7/10 take away 2/10, I've now got 5/10. So if I now pull out 2 lots of 2/10, so 2 times 2/10, I've made 4/10. 4/10 divided by 2 is going to be 2/10. Easy. So who said maths was complicated? So now let's think about what we can do with numbers. I'm now going to show you Cuisenaire rods, and Cuisenaire rods are also very powerful. Let me make a little space here, and I'm going to pull out 10 Cuisenaire rods. The Cuisenaire rods work the same way as Numicon shapes. And this time, when I can see that I've got all my 10 out, tighten it all up. If I've got this now as a group of 100, if I put that one on top, what is that in relation to the group? It's 1/100th, isn't it? Well, 1/100th plus 9/100ths will make 10/100ths, or 0.1, or 10%. So maths doesn't have to be complicated. Now, the Numicon shapes do the same thing, in that they've got this 100 baseboard. And so if I put the shapes on here, I can illustrate that that's 15 over 100 as a fraction. It's also 0.15 as a decimal, but it's also 15%. And one more thing, it's an illustration of GST. So really, when we use illustrated equipment for children and unpack the language, they understand it so much more. So now let's look at the symbols. And this time I'm going to show you 6 plus 4. And all of the words that go with that can be add, and plus. And often as teachers, we use both of them. But what does it create? When I put both of these together, I can see that it makes 10. So what really is adding? Adding is joining. That's what adding is. And what's that? That's subtracting. And that's what that symbol is. So I've got adding and subtracting that relate to each other. So what if I now get out several of these and put these together when the groups are all equal? This is quite interesting. This now becomes multiplying, and this one, when I subtract them, becomes dividing. So there is a connection now with adding and subtracting and multiplying and dividing. Look at that, easy. So when kids come to me for coaching, especially year 9s, and I show them adding, subtracting, multiplying, dividing, they say, well, no one's ever taught me that. And they just take off and they're learning, they love it. But there's one more thing that we have often not unpacked for students, and that's that symbol that was invented by a Welshman. Equals. The lines are of equal length and the lines are equally apart, as like parallel lines. How can we illustrate that? Well, as teachers, we often say that they are the same. So I'm going to put my 4 3s on this side, and I'm going to put my 12 on the other side. And I let them swing a little bit to make sure that I understand this, and I can see that they are equal. They're not the same though, they don't look the same, but they are balanced, they are equal, and that's what the equal symbol means. So we can unpack a lot of understanding for children. Other things we can do, let me get back out this shape here, is straight away, there's area. And if I look more carefully at it, I can now start to think about perimeter and creating something around the edge. But not only that, I can think of these little cubes and how I can think about exponents with numbers, with a cube, and then I can actually cube it, etc. And what's it actually going to look like? I need more than that, don't I? So this is really powerful to help children understand the mathematical language and the concepts that we're talking about. So what would the exponent or the power of that be? Other things we can do, and I'll show you more on slides with that. But I think I've pretty much covered all those. Let's go back now and think about what square numbers are. How about that for a good illustration? And if I make it greater than that, I can discover that 16 is a square number. So let's have lots of fun with maths and unpack that. Let me just share my screen and finish off what I want to share. So we've covered all of these points. So let's think about the beginnings of number, starting with the whole, the parts, 5 ones. That's setting them up for place value, bringing in the word. And then when they see it on a number line, cardinality is the last number counted, describing the group. So we can see relationships quite carefully with numbers when we look at the whole first of all, and then think about the parts. This is different from starting with counting first. We're going to be looking at the whole group instead. Cuisenaire rods do the same thing. Children love to play with them. Now that 6 shape is a representation of 6 ones. So let's think about place value again. I can make 10 with 10 ones and exchange it or rename it. That's why 10 has its name with 1 and 0, because it's 1 10 and no ones. We can show all the teen numbers, and it's the teen numbers that lots of kids don't understand because of the language. Look at the word 19, but we actually write it teen 9. That's often where the challenge starts. And so the Numicon approach starts teaching 19 first, rather than 11 and 12, which don't give children any clues about the structure of teen numbers. Teach them the Gatenio board. Help kids understand the pattern of maths and the relationship of what happens each time with a difference of 10. You can download those from the internet. You can set up the shapes showing integers with positives and negatives. You can create planes and graphs so children understand positions as well as orientation with directions on a map, north, south, east, and west, sectors of numbers. But this is really powerful, thinking about how children think. So let's read this through. Here's the problem. This child says, I'd add 2 to 4, then multiply by 3, it's got to be 18. But this one, you should multiply first, so 6 and 4, more is 10. Doesn't make sense because it could be 10 or 18. And then I think they're both add. One's just wonky, so it's 9. So you see, we all have different perceptions of understanding these algorithms. And that was illustrated in our previous session. So through research, Alan Pavio discovered that when we look at numbers, the representational, the referential aspect and processing only helps children understand what things are. For example, that's a representation of a word. We don't understand it at this point. That's another one, and another one. These are of the same thing, but different languages around the world. But this would help, wouldn't it, if someone said cat, or at least showed you a cat? Then you know what cat is. And often when we talk to children about numbers, if they haven't understood what we're actually talking about, there's no actual learning that's happened. So thinking about the relationships of maths, bring all the language in every day. Think about, now what's the language that's going to be used in my lesson? How can I unpack it? Why is this important? Well, symbols are all around us, aren't they, with maths? And if children don't understand what greater than and less than is, even crocodile jaws being open are not going to help children, especially those with dyslexia or dyspraxia. They won't know which way round they should remember those. So equivalence is powerful. So number trios help us understand the relationships in maths. I'm going to show you some for addition and subtraction and for multiplication and division. And it's part whole thinking. So these are the parts and the top ones are the wholes. So if 7 is the whole, what possible parts could there be? How many ways can I make 7? Well, I can make it with 3 and 4. Now, what about this one? I've got 10 up here. How many ways can I make 10? Well, I can make it with 5 groups of 2, but I can also make it with 2 groups of 5. And similarly, over on this side, I said 3 plus 4, but it could also be 4 plus 3. So where does the subtraction and division come from? Well, they are usually one of the parts is missing. One of the parts is missing. So if children can learn numbers that go together, numbers that work together, rather than having to count them all, it's going to really help them understand relationships in maths. So now let's think about algorithms. Let's think about this problem. 8 plus 4 equals something plus 7. Now, some children may look at that and say, oh, it's got to be 12, or others might say, it's 17, I think. Or they may add this and add that, but they're mystified by 2 things. Why is the equal sign in the middle? And I've got no idea how to answer that. Similarly, many students haven't seen vertical algorithms. It's a real challenge. But we need to unpack what are they actually thinking. So I've created that problem here by using a tens number line. And I've created the problem down below. 8 plus 4, and what does 8 plus 4 make? 8 plus 4 makes 10. So the other piece of information that was provided was the 5. So what's the missing piece of information? What was that pink box? What is X? 7 is X. And that's how children now can unpack that, talk about that, think about it, reason about it. And now they know what that algorithm actually means. So moving along, Anna Svard from Israel has done a lot of research on thinking and communicating that maths actually is a one big wonderful conversation. And so the advice she gives us is to listen to what kids are saying. Invite a noisy classroom where kids are all talking. Provide the mathematical language to explain relationships and patterns, because talking leads to learning. Encourage rewording, telling, explaining, conjecturing, and even making up your own stories about maths and word problems. This is what she says from Bewitched by Language, which you can download at her website. Individualizing mathematics means becoming able to participate in this discourse in a competent way, and not only when conversing with others, but also when conversing with oneself. This is what learning mathematics is all about. Don't you love that? That was really challenging when I first heard that. Use equipment to illustrate what you're talking about in maths, and maybe write out word problems word for word before introducing symbols. So let's have a look at how this CPA Brunner's of Concrete Pictorial Abstract works. Some people call it CRA, being representational and abstract. Sophia's mother baked cookies. The first batch had 26, the next 35. How many altogether? Well, what does altogether mean? It means adding. So let's see what it looks like. There's the first representation, the second. Put them together, rename them into tens and ones, or illustrate the structure of the problem by using bar modeling. Now I know what the total is, and I've understood the problem. So language is crucial, and this is a particular lesson that I took with students, and my opening activity was all about approximate. Did they understand what that word approximate meant? So I gave them all of these words and asked them to sort them into piles of what they knew really well, what they weren't so sure of, and what they really didn't understand. And there was approximate for one group of children. Here's another group of children, and look, approximate is in there as well. But look also what they didn't understand, equal groups of distribution. So you see, don't presume that your kids actually understand the language of maths. Give them these kinds of activities and you'll know exactly where to teach. For example, term-to-term rules for a linear sequence. Well, what's a term? Isn't that talking about 4 terms in a year? And what's linear? Oh, I can see the line in there. But what does sequence mean? So unpack the language. Here's an illustration. Which numbers are changing? Do they understand next, before, and after in a sequence? So get them to build it. Here's the first pattern, ending in a 6, using Cuisenaire rods. The next pattern finished with a 2. The next pattern with an 18. So what's a term? Oh, I think I understand what term means now. I think I understand a linear sequence. I think I can see what's going to come next because I can see what was before. So that's where it's very powerful. Now, within maths, we have these relationships, and children may understand what inverse is, but they'll forget all of these. But if they've used them, and I'm using Cuisenaire rods here, that 3 and 4 coming together, 3 and a 4 coming apart, addition, subtraction, and then multiplying, these threes coming together, and then that 9 being broken into equal groups of 3. That's what inverse is. What about commutativity? Well, it doesn't matter which way around in addition you do it, and in multiplication, the result is still going to be the same. Distributive, breaking up the numbers to be able to work with them. Associative, seeing 4 groups of 5 having equal values of 5 groups of 4. That kind of language can easily be illustrated for students. Now, if you go onto the NZ Maths website, you'll find lots of activities that you can do with Cuisenaire rods. This is fractions at level 3 of the curriculum, and there are great problems there for students to figure out. But they need to reason mathematically. They need to work systematically in a pattern and learn the language. So let's now think about applying this to algebra. Well, just by using this equipment all the way through from year 1, they are doing algebra. So it shouldn't be a great mystery when they get to actually have the formalized part at high school, when they say we're studying algebra now, because they have been all the way through. Let's look at the factors of 10. That's easily illustrated, and now I know what factors are. Now I know what factors of 12 are. And that's why learning about 12 is so powerful, because of the number of factors. We really should be learning the 12 times table. Now, I'm just going to stop there, because one of the challenges that I find with students is they actually don't know what the word times means. So just watch this. How many times did I drop them on the table? I dropped them 3 times. So that's where times is not just linked to a clock, it's also an occurrence that I've got 3 times 4 because I've put them down 3 times, or I've worked with them. So students honestly don't understand what times means. So let's move along now to the next one. I'm just looking for my little arrow. Here we go. So let's think about how to solve algebraic equations when children are learning about symbols. Well, if we've got the 3x here plus the 10, we can see that it results in 28. So 3x plus 10 equals 28. That unpacks the mystery behind it. So we can use a door to show angles. Why not use Cuisenaire rods on gridded paper to show angles? And remember, I hear and I forget. I see and I remember, but I do and I understand. So I hope I've made a good case for you to use manipulatives all the way through to year 12. Language, say it, draw it, use the symbols, use the concrete experience. Then children will know what you're talking about and understand it. So manipulatives work because they help children make sense of arithmetic. They help the teachers see what the children understand. It increases students' engagement and enjoyment, and that's for sure. Develop visual images and understanding, help them work together, solve problems, provide a bridge to abstract thinking. But you still need engagement and participation, and clear goals and clear activities. They're not magic. So let's think about the impact of this. And this was an email I received from a school this week, that children have this wonderful sense of learning, a real change, just by using equipment and a program that sequences the teaching as well. So Numicon is based on the New Zealand curriculum, fulfilling all of it with equipment and teaching resources all the way through. If you want to catch up for students, we're going to look at Big Ideas. Big Ideas is a teaching program written by Steve Chin, who's one of the world experts on dyscalculia, and by using equipment to go with it. We've also created class packs, and I'm running a course soon online on big ideas. So what is maths? It's all about communication. It's all about exploring and generalizing to be able to solve problems. We do that when we go to the supermarket. That's what doing maths is. So thanks for coming. I hope you enjoy improved engagement with your students, the mystery of maths being solved. You can go to the website numicon.co.nz and you can go to our courses page and join up with our newsletter so that you find out when the big